Hey everybody, Mr. Briz here. So this is going to be our second day of solving integrals that are going to lead into an inverse trig function. Yesterday what we did was some of the basics, and this is going to be some of the more difficult, the more complicated integrals that you are going to need to solve. Just to give you a heads up, these types absolutely can show up on our Chapter 7 exam, and at least on the AP exam, these would be some of the harder to hardest type questions that you would see. So, the first example, I'm going to be talking about a bunch of special cases. This first example then is going to involve completing the square. So, this is something that all of you should have learned within the past couple years. And the reason that we want to complete the square is that that will turn something that is not factorable and it will become factorable. So for these two examples down at the bottom, A and B, we want to be able to turn these into something that does become factorable. So just as a reminder, here's what completing the square is going to look like. So for the expression x squared minus 8x plus 2, what we're going to do is we're going to leave two blanks in our expression. We're going to put a blank right after the minus 8x and in front of the plus 2, and then we're going to put another one after the plus 2. And so this is what completing the square will look like then. We are going to take this value here. So remember, this is ax squared plus bx plus c. Sorry, I'm going to write that in a better place. We have ax squared plus bx plus c. We want to take half of the b value. So if we do 1/2 of negative 8, that's going to give us negative 4. And then our next step is we're going to take that value and we are going to square that. So negative 4 squared turns into positive 16. So that means that we are going to add 16 to x squared minus 8x. Now, because we added 16, we have to also subtract 16 at the end because we are not allowed to change the value of an expression. If we were to simplify this, the plus 16 and the minus 16 have to cancel, and that should leave us with what we started with. So that's why we have to subtract 16 at the end as well. Now that we've done this, this first part, this is why it's called completing the square, that is a perfect square. If we were to factor x squared minus 8x plus 16, that would factor into x minus 4 quantity squared. And by the way, here's a really nice thing that will help you if you need to complete the square. Those are always going to match. The half of the b value is always going to end up being the part that ends up in the back end of your binomial there. So that is going to be a useful tip for you. Then the other part we have to do is we just need to finish off the 2 minus 16. We know that that's going to be minus 14. And there we go. That is how we can rewrite x squared minus 8x plus 2 into a form that was factorable. Now for part B, this one unfortunately is going to involve more work. And the reason for that is this note that I left up at the top. Completing the square is only possible when a equals 1. So since we have a 16x squared, that 16 is a big problem for us, and we are going to need to take care of that. So we are going to start by factoring out 16 from every term in this expression. So we're going to be left with x squared plus 4x, and I can hear you all groaning as you see this. We're going to need to factor out 16 from 5, and we're going to get 5/16. I know it's not going to look very nice right now. It will get better at the end. Now our next step is we are going to have to put in the space. We're going to get x squared plus 4x. We're going to leave a blank there. We're going to have minus 5 over 16, and we're going to leave another blank. And we need to figure out what will go into those blanks. So we take half of 4. That should be times 1/2. We're going to take half of 4 and get 2. We're going to square 2 to get plus 4. And because we added 4, we need to also subtract 4. Now this part that we have in the parentheses is now going to be factorable. So we can write that as, sorry about that. We can write that as 16 times x plus 2 quantity squared. And then this second part here, let's get that 4 and let's put it in into a fraction over 16. So now we're going to have minus 5/16 and then minus, well, 4 is the same thing as 64 over 16. So if we simplify again, we can take that negative 5/16 and subtract the 64/16 and get minus 69 over 16. And I told you this was going to work out in the end, because if we distribute the 16 back in, now we get 16 times x plus 2 squared, and then the fraction will go away and we're left with a minus 69 at the end. So that is how you complete the square. We're going to need that then to solve some of the questions in the notes today. So this first example then, this is question 80 from the Thomas book. Also, I apologize for calling that example 18. I'm not sure why I'm starting with 18. But anyway, so what we will do is we have to look at this, and I notice that this part, I hope you remember this then from yesterday's notes, because we have a part that is outside of a square root and we've got a square root in the denominator, you should be able to recognize that this is going to integrate into the arcsecant. So that x squared minus 4x plus 3, this part here, I'm looking at that and I'm thinking, well, that doesn't look like x minus 2 yet. So we're going to have to figure out how to complete the square to change that into a form that is going to be factorable. So we got the x minus 2 in front, and I'm going to take that x squared minus 4x plus 3, and we're going to start going through the process of completing the square. So there we go. I left the blank then after the minus 4x, and I'm going to leave a blank after the 3. Now we need to fill that in. Half of negative 4 is negative 2. We square the negative 2, and that becomes a plus 4. So we need to put minus 4 at the end. Now that we have done that, let's go ahead and start rewriting this integral. We're going to get dx that's still on top. We still have the x minus 2 outside of our square root. And then inside the square root, this part here factors into x minus 2. And we're going to square that. And then the second part, the 3 minus 4, we know will be minus 1. And now this happens to match the form that we need for arcsecant perfectly. If you would like, you could do a u substitution on this. You could let u equals x minus 2. You could let du be dx. And then you're going to be given du over u times the square root of u squared minus 1 squared. You could do that if you want, or that part is actually not necessary for this because our du ends up just being dx. We could just integrate straight into arcsecant if we wanted. For this, I'm choosing not to. So then we're going to have, if we were to integrate now, we're going to get, so our a value is just 1, so 1 over 1 in front. Arcsecant of u over 1 plus c. And we know then if we simplify and we substitute, that turns into arcsecant of x minus 1 plus c. All right. So now that we've got that, I want you to try these two questions here. Both of them are going to involve completing the square. The first one, part B, I am going to point out that's going to be a little tricky. My hint for you is you need to factor the negative out first, then you complete the square, and then finally you're going to have to distribute the negative back in. That one is a little tricky. I do think that the second one might be a little bit easier. One thing just to point out as well, this first one is actually on the homework too. So go ahead, pause the video, give this a shot, and then when you are done, start the video again and I'll demonstrate how to solve these. Okay, now that you have tried these, I'm going to show how to solve them. Again, my hint at the beginning was that the part that's inside the square root, I recommend that you actually factor out the negative first. So let's rewrite this as negative, and if it's easier for you to see this, you could switch it into standard form, as in putting x squared first, and then minus 4x, and then plus 3. I will warn you though, just because I know what the answer is going to be for this, you're going to end up having to do a little extra work just to get your answer. So I'm going to do this as well. It would have been better if we kept it as negative 3 minus 4x plus x squared. That seems a little strange, but I don't think it's going to look as familiar if we tried solving it like that. So I'm going to instead solve it in the way that I've kept it right here. So when we solve this now, let's complete our square. We've got x squared minus 4x, and we need a second set of parentheses actually. And then we need our plus 3. We know then from completing the square that we are going to get, just like before, negative 2 is half of negative 4. We square that, we're going to get 4. We need to subtract 4 from this side as well. Now what we will have is the integral. I keep forgetting dx, sorry about that. Now what we're going to have is negative, and I need another set of parentheses again, x minus 2 quantity squared, and then minus 1. And this was what I was saying earlier about the hint that you want to distribute the negative. Also why I was telling you that it may be easier if you kept it as 3 minus 4x plus x squared. When we distribute our negative, let me get this, I need some space here. When we distribute that negative, we're going to now rewrite this, still forgetting dx. We're going to rewrite this now as 1 minus x minus 2 quantity squared. And I hope you can realize that this is going to integrate into, since that's a 1 squared there, this is going to integrate into arcsine. We're going to get x minus 2. And we just include our plus c, and there is our antiderivative. Okay, now on to part B. So B, unfortunately, has an a value that is not going to be 1, and instead is going to be 9. So we're going to have to factor that 9 out in order to solve this. So, sorry, I'm zooming in a little too much there. We're going to start with 1 over, we're going to take the 9 out. And I know that 12 over 9 is going to be a little obnoxious. Let's simplify that then into 4/3. And then the 8/9, we can't really do anything about that, so we're just going to keep it like that. Just to save us a little bit of space and a little bit of time, I am going to actually put in my spaces here when we complete the square. And now half of 4/3 is 2/3. And be careful, when I first made my notes, I messed up this part here. If you square 2/3, it actually becomes 4/9. So then because we added 4/9, we have to subtract 4/9 as well. And as usual, I'm forgetting dx. Okay, now that we've got that, let's go ahead. Maybe I'll fix this by putting dx on the top. Now I can't forget it. Okay, so we've got our 9 in front. Now we know that this first part is going to factor into x plus 2/3 quantity squared. And then the second part, the 8/9 minus 4/9, that is going to turn into 4/9. And let's see. You know what? I actually did something wrong here. Instead of that, what we should do is we should distribute the 9 back in before we factor. So by distributing the 9 back in, we're going to get 9x squared. Then the next part, 36 over 3, is going to give us 12x. Then 9 times 4/9 is going to give us 4. And then the last part is we're going to get a plus 4 at the end. And the reason that we wanted to distribute that 9 back in is because this part here is still a perfect square. The way that I know is that if I look at the first part, 9x squared, the square root of that is 3x. And the second part, that 4 there, well, the square root of 4 is 2. So we can still factor that into a perfect square. Then I've got the plus 4 at the end, I've got the dx on top, and we're integrating. And I hope that you see that this integral is going to become arctangent. What we have is our u value right there, which is squared. And then we've got our a value here, which is squared. There's just one thing that's missing, though. And I think u substitution is going to help you see what that is. What is missing is that if u equals 3x plus 2, du has to be 3 dx. We don't have that 3. We need to introduce that. And if we put the 3 in there, we need a 1/3 in front. And now we can change this into 1/3 the integral of, let's see, that will be du on top. And on bottom, we are going to get u squared plus 2 squared. And really, for arctangent, it's not that big of a deal, but for some reason, textbooks love writing it where it's a squared plus u squared rather than u squared plus a squared. So I'm just going to rewrite it like that as well. Then, when we continue, now we're going to find our antiderivative. So 1/3 arctangent of, and then we are going to need to have u over 2 plus c. And our final step here is that we just need to substitute 3x plus 2 back in for u. And there is our answer, 1/3 arctangent of 3x plus 2 over 2 plus c. Now, there's one thing I wanted to point out. I can imagine that there's a question, and honestly, I kind of struggled with this too myself. Some people, you probably know that in the front, you know what? I'm sorry. I was saying that there's a common mistake, and I just made that mistake again. I guess I owe everybody another $1 for pizza. So, remember that in front of arctangent, we are supposed to have a 1 over a. I remembered this 1/3, but I forgot the 1 over a. I should have had a 1/2 there. And for this last part, our answer, I should have had 1/6. So my apologies. Sorry about that. I think I am now up to $12.50 for pizza. Here, as proof. $12.50 for pizza. Okay, so that was our first special case where we had to complete the square. Now we're going to get into our second special case where we need to multiply the top and bottom by this fraction ax to the nth over ax to the nth, which you should see, of course, is just 1. Now, this first example that I've got here doesn't exactly need to... I'm kind of stretching the definition a little bit by saying that we need to do the special case, because it's really not that big of a deal, but the second one definitely needs it. So for our first one, I'm looking at this, and once again I'm spotting I've got something outside of a square root, and that's telling me that we're going to need to integrate this into arcsecant. But the other thing is, I notice these two things are supposed to match according to our definition of the integral that integrates into arcsecant, but that doesn't actually match, because if I write this out, I'm going to show you, we're supposed to have a value, and then we need the square root of 4x squared, which is 2x, and then we've got the minus 3 squared. So what I'm noticing is that our 2x doesn't match what we're supposed to have out in front, because that's just an x. So what we need to do, one thing is that u substitution would kind of fix this anyway. Well, not really. I suppose it does actually match this here, but anyway, the point is, what I'm trying to get you to see is that this is supposed to be u. This is also supposed to be u. They don't match. So that means that we're going to need to multiply that x in front by a 2. And now that is going to be u. And because we multiplied the denominator by 2, well, according to this rule, we need to multiply the numerator by the same value. Now, normally when we've done this for u substitution, we've taken that value and we've just put it out in front. But in this case, that's actually not going to help us, because we need the derivative of u up on the top. And if u is going to be 2x, well, its derivative is going to be 2. Sorry. Its derivative is going to be 2. So we need that 2 dx up on the top anyway. Now that we have written our integral like this, we are able to turn it into arcsecant. So this will become then, let's see, we need 1 over a in front. So 1, here's the a value, so it's 3. We need arcsecant. It's u over a, and then plus c. And there we go, that's the integral. All right, now for this second one, I want you to try this on your own. I'm going to give you a hint. You need to multiply by a variable, because notice ax to the nth, it is possible you need to multiply by x. So pause the video, give that a shot, and then I will demonstrate how to solve it when you are done. Okay, now that you have tried this question, I'm going to show you how it's done. So this one, again, is going to integrate into arcsecant just based off of the fraction. And what I noticed then, when I split up that part that's inside the that part that's in the square root, our u value is x squared. This time, our u in front, though, is only an x. Well, that's not actually u, it's the square root of u. So we need to introduce another x so that it does match. And because I multiplied the denominator by x, sorry, I should pick a different color for that. Because I multiplied the denominator by x, that means that I need to multiply the numerator by x as well. And that takes care of the ax to the nth that we needed. Now that I've done that, this does match what we needed for arcsecant. So our integral, this 16 here is supposed to become a 4 squared. So then 1 over a is 1 over 4. We have arcsecant of x squared over 4 plus c. All right, our third special case then is going to be long division. So something that you learned back in IM3. By the way, I said this at the beginning of the video, I strongly encourage you to remember these four special, well, not the fourth one. The fourth one is bad, let's just be honest. But the other three, the first, the second, and the third ones, where we had to complete the square, we had to do ax to the nth over ax to the nth, long division. Those you definitely should remember for the Chapter 7 exam. So remember for Chapter 7 periodic, special case number 1 through 3. Again, number 4. Number 4 is if I wanted you to fail the exam. Let's just put it that way. So what we're going to do here for long division then, now we have to be careful with the denominator. T squared plus 1. Back when we did long division in IM3, a common mistake that people would make is that they would forget there's a 0t there. So make sure you include that 0t when we do long division. And when I demonstrate this, you're going to understand why we need that. Okay, so we're going to go ahead and put in the numerator and the denominator. Now we have to figure out what is going to multiply with t squared to make t cubed. And we know that's going to be t. Now we have to multiply this t by t squared. And we know that that's going to become t cubed. Then we need to multiply t with the 0t. Well, that's just 0t then. 0t squared. Then we need to multiply this t with the 1. And that's going to give us a positive t. The last thing that we do for long division is we're supposed to subtract this entire thing down below. T cubed and t cubed cancel. We are left with negative 2t squared. We have 3t. Be careful, it's minus a positive t. So it's going to become plus 2t. And then lastly, we drop down the minus 4. Okay, then the next thing is we are going to go to, let's see, we need to figure out what is going to multiply here, once again with t squared, to make negative 2t squared. And we can see that if we put in a minus 2, negative 2 times t squared makes negative 2t squared. Then we multiply it with the 0t. And finally, we multiply it with the plus 1. Now be careful, we need to subtract. Negative 2t squared minus negative 2t squared, those cancel. 2t minus 0 is going to become 2t. And then negative 4 minus negative 2, that becomes negative 4 plus 2, that's a minus 2. And this here cannot be divided by t squared because t squared is bigger than that. So that will end up being our remainder. And I'll put that up here at the top where we have plus a 2t minus 2 all over. And then we're supposed to divide it by what we were dividing at the beginning, t squared plus 1. So here's the bad news. That's only about half of the work that was necessary. So now that we have taken care of our long division, we are going to rewrite the integrand to match what we've got up here from our division. So that's going to give us the integral of t minus 2 and then plus 2t minus 2 over t squared plus 1 dt. We are going to split this up into multiple parts. So I notice we can integrate t minus 2. So let's go ahead and put that into its own integral. Now, this second part, the fraction, I spot, and it helps that I know what the answer is going to look like. We should actually split that into two fractions. So it's going to become 2t over t squared plus 1 dt. And then the last fraction is going to become negative 2 on top with a t squared plus 1 on bottom dt. Sorry about that. Plus 1. Okay. So the first set of parentheses, the first integral, we already know that that's going to become t squared over 2 minus 2t. That part is done. This second integral is going to require u substitution. U is t squared plus 1. Du is going to be 2t. And then for this last part, what we should do is we should factor out that negative 2 and put it in the front. And I'm hoping that you recognize that this integral is going to become arctangent. So if we were to do that u substitution on our middle integral, we then are going to get 1 over u du. And then for the second part, this here, as I said before, we know that that's going to integrate into arctangent. We are going to have t over 1 inside. And I suppose if you want to be really picky, I should have remembered the 1 over a, even though that's just 1 over 1. And then the last thing is, I've got a little bit of space. I'm going to try to squeeze in a plus c there. There we go. Okay. Don't worry, we're almost done, I promise. So the first part, we keep t squared over 2 minus 2t. Then we're going to have natural log of u, and then we are going to get minus 2 arctangent of t plus c. And finally, the last step is we just need to replace that u that's in the natural log. And so we are finally at the end for this. T squared over 2 minus 2t plus natural log. Because t squared plus 1 is always positive, we don't need the absolute value anymore. And then minus 2 arctangent of t plus c. This is probably the hardest question involving long division that you would see then on our, not just involving long division, but this is probably the hardest question you would see with an inverse trig function that you would see on our exam. And now finally, I just wanted to show you one more. I promise you this will not be on a periodic. This is going to be bad. Let's just put it that way. Special case number 4. Good luck. You're going to need it. Insert evil laughter here. So the reason why this question is so bad is because it requires something that you probably won't recognize. Even after I show it to you, I don't think you would always be able to recognize this if I gave you another question. In order to solve this, we don't just need to split up this into multiple fractions. We actually need to take apart 4x plus 7. And how we're going to do that is we're going to start, I think a good hint is if we can start with a u substitution. So I'm going to start by just saying u equals x squared plus 2x plus 2. Therefore, du is 2x plus 2 times dx. Now, that doesn't take care of everything. Because you may be thinking, oh, well, now that 4x plus 7, we should just figure out how to take out 2x plus 2 and we're good. It's not quite that easy. Instead of 2x plus 2, we're going to take out 4x plus 4. This is why I'm saying good luck, you're going to need it. Not because it's difficult turning 2x plus 2 into 4x plus 4, but because we're going to need to turn the 4x plus 7 into a 4x plus 4 plus 3, and then we're going to put all of that over x squared plus 2x plus 2. And this is where we split it up, not into 3 fractions, but into 2 fractions. 4x plus 4 goes into the first one. And then we're going to put 3 over x squared plus 2x plus 2 into the second one. Here's where it starts getting, believe it or not, worse. I'm noticing for the first one, this won't be so bad. It's still going to be just use substitution. We needed 2x plus 2. We actually have a 4x plus 4. Okay, we're fine. We can take care of that. We just need to take out 2, turn that into 2x plus 2. Okay, we're good. That's fine. This is the problem. That doesn't match any of our forms. We're going to need to complete the square on that. So the first one, the first fraction, the first integral, I'm sorry. I'm just going to go ahead and switch that into u. And then for our second one, we are going to need to start completing the square. I'm going to move 3 out in front. We got dx on top. We're going to get x squared plus 2x, leave a space, plus 2, leave a space. Completing the square, half of that is 1. We squared, it's plus 1. You have to subtract 1 at the end. Now we are going to get 2. I'll integrate that into natural log of u. Then we're going to have plus 3 integral of dx over, and that will turn into x plus 1 quantity squared plus 1. And I'm going to write that as squared as well. And you should see that this is going to integrate into arctangent. So we're going to get 2, I'm going to replace my u there, so 2 natural log of x squared plus 2x plus 2 plus 3. Fortunately, our a value is 1, so it's just going to be 3 times 1 over 1, which I'm going to leave as 3 because as you can see, I'm at the bottom of the page. I can't go any further. It's going to be 3 times 1 over 1, which turns into 3, arctangent, and inside it's x plus 1 over 1, which is just x plus 1, and then finally plus c. We are done. So here is the assignment. By the way, I should actually note, I changed the assignment a little bit on Schoology, so you should actually disregard those questions. So you are aware, I think this is the most difficult thing you will do all year. It might be debatable for some people. You might find something else that we've already done that's more difficult. Maybe something in the future is going to be a little harder before the end of the year. I think this is the toughest thing. So that's why tomorrow we're not going to have anything new. I'm just going to let you have more time to work on this, give you a little more time just to think about it, and it's going to be that. So